So we're lucky to be joined today by Dr. Stephen Morris. He is the J. Tuzo Wilson Professor of Geophysics at the University of Toronto. He has a BSc and an MSc from University of British Columbia, his PhD from Toronto, where he's been, I think, for a while, 10 years, 15 years, if I...
Forever.
Yeah. He's been there for almost forever and has won 2 teaching awards at Toronto. Also has been a visiting fellow at Cambridge University and is a fellow of the American Physical Society. At Toronto, he directs the Experimental Nonlinear Physics Group, which, according to its website, not only does he direct, but he's also the chief fundraiser and receptionist for that group. So wears many hats. So anyway, thank you for joining us and taking the time to talk to us today.
Hello.
So I want maybe to start off, if you could talk a little bit about what drew you to nonlinear dynamics or chaos in the first place? How did you get involved in whatever it is you're involved in?
Well, I started out a long time ago working on liquid crystals, which are a kind of soft matter topic, a material science soft matter topic. And what's interesting in liquid crystals are phase transitions. So you change the temperature and the liquid crystal goes into a different phase. Liquid crystals are very visual. You can look at them under the microscope or with your eye, and you can see their phase transitions nicely. And it's kind of a short step from there to pattern formation, which is the nonlinear dynamics of systems, where if you drive them with some kind of force and you increase that force beyond some threshold and a new pattern emerges, that's a bit like a phase transition.
Yeah.
So in fact, the theory of phase transitions and the theory of bifurcations in nonlinear systems are really close cousins of each other. And the experiments are even fairly similar, although one of them is an equilibrium system, the thermodynamic system, and the other one is a non-equilibrium system. But it turns out that's not so important. Basically, the experiment is quite similar. You can look at transitions between systems in patterns by changing a parameter, and you can take pictures of them and write theories of them, and it's really quite similar to condensed matter physics. So many people of my generation who do pattern formation came here from condensed matter physics originally, and especially soft condensed matter physics. So that's how I got started on it.
Yeah. I wonder, my background in grad school, I was starting with high energy theory, which I enjoyed the math of, but it seemed to me to be getting sort of farther and farther removed from reality. And one of the things that drew me to chaos and nonlinear dynamics was it was, to some extent, the physics of the everyday.
Yes, yes.
It sounds like that also has been a theme in your work as well.
Absolutely. I really like the visual aspects of it. I like being able to make experiments out of simple parts, and it's very easy in this field to just walk down the street and see something and then go in the lab and make an experiment out of it. It'd be the first one ever done.
Yep.
It's almost the exact opposite of the LHC. LHC is bigger and bigger and more expensive and more people, and takes longer and longer to do the experiment. And in this field, it's really the most exalted things are simpler and simpler and cleverer and easier and easier.
Yep.
They all involve just one person.
So
usually one graduate student gets to build the first and last experiment and understand a phenomenon for the first time.
Nice. Yep.
And that's really attractive.
Yep. And to me, at least, I always felt that even though they're sort of everyday and simple phenomena, the mathematics behind them was no more or less beautiful than the mathematics behind string theory. Right. Maybe more so because it actually describes the real world. String theory, maybe.
I think it more so, yeah. And it's often very difficult. One reason why these things weren't done before is in fact that they are difficult.
Yeah.
We still don't understand a lot of what seem to be everyday phenomena, and the reason is they don't fit the standard paradigm of Hamiltonian, equilibrium physics that we tend to teach people. We tell first-year physicists that friction's, just a kind of annoying extra force that we should try to ignore or get rid of in our equations and so on. But the truth is that it's an enormously powerful organizer of phenomenon, and you can't understand fluids without viscosity, and you can't understand motion without friction.
Yep.
And so, it's crucial. So, and many times these things were looked at with the tools of 19th century physics ages ago.
Yep.
But those tools have been enormously improved, and we have all kinds of new ideas, a lot of them brought from condensed matter physics. And so it's, on the other side, experimentally, we have vast tools that we didn't have before, even just digital cameras, for example.
Right. Yep.
The idea that you can now follow thousands of icicles, whatever you're studying, and just analyze, images, which could not even have been, you couldn't afford to take that many images before.
Right. Yep.
So it opens up, it's like big data. We suddenly have big data on everyday phenomena, which
right.
we didn't have before. That means the laboratory experiments can be very sophisticated because all I'm using is a commercial SLR camera and a computer.
Yep.
But those things are very powerful now compared to where they were even 20 years ago.
Sure. Yep. Is there an experiment in pattern formation? One of these, one grad student, one tabletop sort of thing that is particularly maybe that you could describe to us a little bit? I'm thinking about icicles because I'm looking out my window and there's still ice everywhere, but
well,
it could be icicles or something else.
I have an icicle experiment. This is one that I've been working on right now, and it's exactly what you would think it is. It's a tabletop thing. It's a big fridge thing that we built on the tabletop,
yep.
and it produces a small region of -10 or -20 degrees Celsius. You dribble water in the top with a peristaltic pump, so we know the rate of water flow.
Yep.
We stir the air inside, and we carefully control all the conditions inside, and we grow an icicle. And then there's a slot in the side of the box that we point a camera in there, and we follow the growth of the icicle over many hours. And we can use the digital image to trace the edge of the icicle as a function of time. And so we know exactly, and we weigh the water that runs out, and we measure the humidity, we measure the flow of air in the box. So we can produce icicles under completely controlled conditions.
Yep.
And this has almost never been done before. There are a few experiments where people made icicles, and they basically measured their length and width, and they did sort of a gross how much ice is there calculation. But the question of what shape is an icicle is a quite subtle one. And this is an example of a moving boundary problem. So you have an interface between ice and air, ice and water and air. And you need to write down differential equations or models for the motion of that interface. And so the outcome of the theory would be some kind of time history of the shape of growth and length and shape of an icicle, or any amount of growing ice, for example. And this turns out to be incredibly difficult. No one's ever done it. It's much more difficult than you would think. And there are surprises. So, for example, the ripples icicles have ripples on them. Many icicles, if you look out your window, you might see some that have a kind of bumpy texture.
Yep.
It turns out that those ripples are weirdly universal. They're almost exactly 1 centimeter in wavelength everywhere in the world, always the same. Independent of the temperature, the water flow rate, everything. No one understands why those ripples are there. Mm-hmm. There are also ripples on stalactites, which are kind of the rock ice things that hang from the top of the cave. And they grow in a similar but not exactly analogous way. Water runs over the shape, so the flow of the water determines the shape, and the shape determines the flow of the water.
Yep.
Feedback, and the ice, and for some reason which we still don't really understand, the ripples also form on stalactites.
Yep.
So we're often looking for what are called universal or universality among patterns.
Yep.
For example, a rippley pattern that you see is often driven by quite different underlying physics, but basically they're all ripples. They all have the same symmetry. They all have the same kind of defects. Ripples generically move in the direction of the driving force and so on. So, for example, ripples on icicles actually move upward slowly as they form. This wasn't really well known before we did the experiment.
Yep.
So the experiment is quite simple. It sits on a desktop, and it's the size of a fridge, and we built it.
Nice. So one of the things, when I think a little bit what's different about chaos or dynamical systems maybe than other areas of physics, is a little bit, I don't know, maybe some of what you were just describing. And so if you were trying to come up with a model for icicle formation or stalactites, one approach is to start very detailed with sort of all of the basic physics. But another is maybe to start at a slightly higher level and say, well, just like you were saying, there's something common about ripples. So let's see what we can learn about ripples independent of whether they're ripples in water or stone.
Yes.
And that to me feels like something that has a different flavor about nonlinear physics, the sort of work you do in chaos and so on. Does that sound right to you?
Yes, that's right. Many times one can qualitatively reproduce a universal behavior using what are called model equations, which are often simply guessed from symmetry. They're kind of like the standard model of particle physics is just a Lagrangian that's guessed by guessing the symmetry first.
Yeah.
And you can do those kind of models in patterns. If you know the symmetry, you can write down the basic equations.
Yeah.
And often that's enough. You don't really need to do a detailed model of the underlying physics. The model equations often contain all the dynamics that patterns have in them for many different systems without any more work, in a sense.
Right.
So that tells you that the features of that pattern are generic. They're not related to the underlying physics directly. They emerge directly from the model level equations.
Yep.
And this is somewhat analogous to what people do in phase transitions or in condensed matter problems, where they use what are called coarse-grained approximations. So rather than write down the Schrodinger equation for all the atoms and so on, you write down a simplified Hamiltonian or whatever, which contains just a few degrees of freedom, and you hope those are the ones that are relevant.
Yep.
And the argument always is all the other ones will just be averaged over or disappear in the final model anyway. And it's quite common in condensed matter physics to make models of that kind as well.
Yep.
So we work in a style which is inherited from condensed matter physics in that way.
Yep.
Where an argument that leaves out most of the details is considered elegant and simple if you can recover most of the phenomena with few adjustable parameters and a model which is minimal in some sense. That's often considered to be a better way to approach it than the kind of brute force, let's compute everything method.
Yep.
In the earth sciences, in climate and in geography, physical geography or geophysics, it's often a kind of all singing, all dancing giant computer model that people tend to go for. That has the feature that it often accounts better for the phenomena in detail, but it's monstrously more difficult to understand. You kind of run it and output comes out, and you hope that it's right, kind of thing.
Right. Yeah.
And you do your best to tune the parameters to be realistic, but that's just a different way of working.
Yeah.
We tend to favor the simplified picture.
Yep. Yep. No.
So thing that has ripples has the same ripples at that level.
Yep. Yep. Absolutely.
We say, why is an icicle long and pointy? Well, for the same reason as a carrot is long and pointy. The tip grows faster than the sides.
Right.
And if you write, a simple scaling relationship between the way they two grow, you can predict the shape approximately.
Nice.
There is such a theory of icicles and stalactites too.
Yep.
And carrots, if you kind of stand back and look at it, it's also a theory of carrot.
Huh. Nice.
So it's you don't try to explain everything about the thing. You just want to catch the what we call the crucial, relevant physics.
Yep. Yep. Which is, I think, a very nicely complementary approach to that. Let's come up with a big model that you can use to predict the way these giant climate models are as well.
Yeah.
I wouldn't want to throw those out, but I think having both is a better
they have
situation.
different purpose.
Yep.
They're not trying to understand the climate. They're trying to predict it.
Yes.
Which isn't the same thing. If the computer goes through a mysterious process and correctly predicts the climate, then we don't care what the process it does is, in some sense.
Right.
We don't need to know why.
Exactly.
As long as we believe the output is correct.
Right. Yep. Yep.
Whereas we're in a different game where we want to know why.
Yep.
And that means it has to be simplified to the level that a human can explain it to some other human.
Right.
And that just means a big computer calculation can't always do that. Right?
Yeah. Yeah, for sure. So one of the things, looking at your work, both your videos on YouTube and the photos you have on Flickr, and I'll post links to them below the video on the Complexity Explorer site so folks can check those out. It seems like you're drawn also to there's an aesthetic component to some of what you're doing. That you,
Yes.
there's just a sense of fun that you just like these things and you like when other people like them.
That's right. I've always secretly, I suppose, always done it for that reason.
Yeah.
Just because I like the look and feel of the thing.
Yep.
And it's not a scientific motivation of the standard sort, I suppose.
Yep.
Although we often hear from string theorists that they work for the beauty of their equations.
Yes.
I work for the beauty of the phenomenon, and I have a very specific idea what that is. I know it when I see it, And recently, in the last couple of years, I've kind of come out of the closet and waved it around a bit more. So I've actually put a lot of my pictures and videos into art gallery contexts and in other places. So basically to just appreciate them for their aesthetic content, or maybe for their sort of humorous, surprising content.
Yep.
Watching the chains, if you link to the video of the chains dancing around and making little spirals, it's hilarious, I think. They seem to be dancing to the music,
Yep.
And it's still kind of, surprising. Why the heck do they do that? And we can go and do science on that, of course, but we can also just appreciate it for what it is, and
Yep.
and for maybe just for the sort of human element of it. So I've done a lot of that recently. I have what they call an art practice, which is another limb where I repurpose my scientific pictures and a lot of other pictures which aren't made in the lab.
Yeah.
I repurpose them for as photography, as art photography.
Yep.
And
one of the things I'm hearing you talk reminds me. On a couple of occasions, I've had students in my classes build chaotic water wheels.
sure.
So, which we actually haven't talked about in this class, so let me just explain briefly. This is a mechanical analog of the Lorentz equations, and it's a water wheel with leaky buckets that spontaneously reverses itself.
Mm.
And I find when these students, and these are just rigged up with bicycle wheels and hoses and plastic party cups. They're not sophisticated experimental devices, but when the wheel is going in one direction and when it does the first term, there's usually spontaneous laughter.
Yes.
It's just I've always wondered, like, I think it's just enjoyable maybe to see something that looks mechanical and clockwork.
Yeah.
Just screw with you.
Things, yeah. Well, another one I often do is the double pendulum. It's like a double jointed pendulum, and it looks like a person waving their arms wildly. Yeah, and I think people are attracted to things that do surprising things, either mechanically or visually. And nonlinear systems, that's just what they do.
Yeah.
Chaos, it looks like something important is, it looks like something is happening of its own free will there in some way.
Yeah, absolutely.
If the wheel reverses, it's making some kind of human-like decision.
Yep.
And we know that it's not, but it's still surprising and kind of funny.
Yep. And I think, yeah, and it's fun, I think, to think, particularly in terms of pattern formation, that, yes, the icicle isn't trying to be a pattern, but that one can get these very pleasing and interesting patterns sort of from nothing, that's just built into the world, I think is a really fun realization, for me at least.
Yeah, it's sometimes called self-organization.
Yep.
So that implies in some weird way that the icicle has a self.
Right. Yes.
We don't think it does, but
probably, who knows? Who are we to say?
Somewhere down there.
Yeah.
So it's called self-organization because there's this intuition that it decides what to do, and it's not imposed upon it by some outside force. And that's a kind of appealing idea, I think.
Yep. No, absolutely.
You don't believe it has a self or an opinion or
a... So the last sort of thing I'll be interested in hearing you talk about is I noticed that you have at Toronto a course called Emergence in Nature, which looks like a course maybe somewhat similar level, maybe even a little less math than this course, on a host of topics in pattern formation and nonlinear dynamics. And I'm curious what drew you to teach that course and what your experience with that has been.
Well, I designed the course precisely because I wanted to teach that kind of thing. Yep. So I wasn't drawn to it. I made it from scratch. The central idea of the course is, and it's a breadth course. There's no math in it at all.
Right.
The central idea is there is this standard way of doing physics of reductionism, where you take the thing apart until you get down to the standard model of particle physics or something like that. And the central idea of the course is the great chain of being, the idea that there's this kind of railroad from the most complex thing down to the very simplest thing, and we always descend in reductionism. And the idea is to see what it's like to go the other way, to build up and see how things are explained in terms of the previous level of description. And so we do talk about particle physics, and I emphasize how the proton emerges from the strong interaction, and how nuclei emerge from the nuclear forces, which are somehow related to the strong interaction, and we build up to atoms and molecules and life, and sort of an anti-reductionist approach. So the idea is to emphasize the kind of build up of complexity from the simplest explanation. And the idea of how much you have to put in to do that. You can't just reduce things and then stop and say that you've explained everything.
Right.
The origin of explanation is much more involves going up and down the chain all the time.
Yep.
And there are many phenomena which are really only comprehensible at some higher level of the chain. Like we talk about emergent patterns, and we talk about emergent social structures and networks, and self-organized criticality, which might be something that you talk about, and all of these ideas. And nonlinear dynamics is in there, and pattern formation is in there, but so is a lot of other things.
Sure. Yep.
And it's an attempt to kind of break the standard model of breadth courses, which is kind of, I'm sure you probably teach one, where it's like physics 101 has always got the same topics in it. We always talk about the Greeks and so it's an explicit attempt to go the wrong way up the highway of the
Yep. And how do students react to that? What's the response been?
There's about 100 people in it. Well, University of Toronto is very large.
Yep.
So I get all kinds of reactions. It's usually taken by humanities students, and they come from a huge variety of backgrounds, including music and architecture and all sorts of things. And so they take away from it something related to their own background, which is often quite surprising. Every year I let them do one of the writing assignments. They have one of the options is do something creative, like make a song or a poem or an opera or something like a sculpture or something.
Yep.
And a few students produce hilarious YouTube videos of sonnets that they've written about the standard model of particle physics.
Nice.
So the answer to your question is, it appeals to students who are immersed in some other field to take ideas from physics and kind of put their other field in that context. If you talk about emergent systems, you were talking about just about everything, so that everybody gets something out of it.
Yeah, I teach a class here. It's not centered around emergence, but chaos and fractals.
Right.
And similar thing, I have students. Fortunately, here classes are small, 15 to 20, and students do a final project, and they can pretty much do anything. And over the last 10 years, I think they have pretty much done just about everything possible, from sort of standard presentations to poems, sculptures, plays, puppet show. I mean, just all sorts of things. And it's really fun to see how people can take these ideas and apply them in ways I never even would have imagined. Yeah,
well, that's part of the process of kind of assimilating stuff. You have to come at it from your own. The teacher cannot just impose a point of view on you. You come with one.
Right.
And so it helps to be talking about phenomena that are more directly connected to experience, so that a musician can think about the instrument,
right,
which is the thing they know really well.
Yep.
And I also do, fractals and other things, but it's all in a long narrative which is connected together by this idea of just going upscale.
Yep.
But we end up talking about most complex systems having first talked about the supposedly simplest ones.
Right,
like fundamental particle physics.
Yep.
And then in the end we talk about social systems and consciousness and the prisoner's dilemma and stuff.
Yeah, yeah, lots of grist for the mill.
Exactly.
There, and it's often such a change from the often dreadful science classes they've had that.
Yes, I hope so.
Yeah, sounds like it.
It's usually the only physics course they ever take in their lives because they're humanities students typically.
Right.
They may be taking it in high school, but that's all.
Yeah, yeah. I've always felt that if somebody's only going to take one math or one physics class or one science class, it ought to be about the really best and most interesting stuff.
Yeah.
And, so often, at least in the U.S., students, their last math class is pre-calculus.
Yeah.
Which just seems so it would be like if your last literature class was pre-Shakespeare.
Yeah.
You're not even allowed to learn Shakespeare. You have to take pre-Shakespeare and then say, oh, no, you're not good enough. Go away. So, yeah, I think we really need more classes that expose students to the really good parts of math and physics.
Yeah. And of course, because it's a qualitative course, we don't expect them to become experts, and
right.
And all the assignments and all of the readings are non-mathematical, and so I encourage them to say what they really think of it, not to write an essay as if they knew what they were talking about necessarily, but to tell me what you think of this topic.
Yep. Excellent.
So, yeah, it's a fun class.
Great. Sounds like fun. Are you gonna teach it again? Is it on your rotation?
Right now, it's being taught by someone else.
Uh-oh.
Not the books. Well, we have a very large, cycle of courses.
Sure. Yep.
Right now, I teach second year mechanics, which allows me to talk about chaos and even fractals and stuff within second year mechanics. And I use Python.
Nice.
And the students have to learn Python, and so they do mechanics with Python. And at the end of the course, we're doing the Lorentz model and all that stuff, mechanics.
Yep.
And they integrate the stuff with Python.
Excellent.
So
excellent. Sounds very good. Well, I think that about wraps it up. We've kind of covered the things I wanted to cover. Thank you very much for your time and your thoughts. And I don't know if I'll ever get to take your course someday, but I look forward to seeing it unfold. And I'm glad to know there are others trying to get these ideas sort of swimming in the wrong direction of reductionism, trying to spread that word a little bit. So.
Yeah. Okay.
Thanks much.
Okay. Bye-bye.
Take care.